It's really, really nice to be back here. Just moved 4 months ago, and I already miss it a lot. And it's good to see all these faces again. So thanks for having me. As the title of my talk suggests, I'm going to talk about managing resources in agriculture. And one of the greatest issues of our time, I would say, is the pollution related to agriculture. And not only that, the effects of climate on agriculture and food production has the potential to create one of the greatest humanitarian issues of our time. And because of the gravity of these issues, I'm sure you're all very well of, I'm just excited here to come and talk about it and provide some overview of the work that's been done to illustrate these issues, and to provide some information about what I'm working on with our group and solutions and technologies that we're developing to try to enhance efficiencies in agriculture as well as sustainability. But before I move on, I really want to emphasize all of the great people that I've worked with that have collaborated in this work and have taught me to and have allowed me to be in the place that I'm in now. So I'm sure many of you have heard the news and on the radio about all the controversies and blame being put on the agriculture sector as this drought has been playing out over the last several years. And I think a lot of that has to do with the fact that there's been a lot of calls, especially in California by Governor Jerry Brown, to limit water use in the residential sectors. And there hasn't been a lot of clear information about how the agriculture sector is being affected by this drought and how they are limiting their water use during these times. And so what I think it's important to take a step back, and what I'd like to do is just kind of go over, provide some information about the issues related to resources used in agriculture, and present some possible constructive options for trying to improve the problem. And so many of you probably know that the United States is the second greatest producer of commodities in the world in agriculture. And of the 12 greatest, the top most produced vegetables in the world, the United States is in the top 5 for producing 7 of those vegetables. And California alone produces 15% of the total production of agricultural goods in the United States. And finally, California's 78,000 or so farms generate $46 billion of revenue. And in the United States as a whole, there's about $790 billion produced. So you can imagine that, this is agriculture in California and the United States as a whole is very important for feeding the 7 billion plus people in our world. But as you can imagine, to produce all this food, there's a big take on our resources. And since we all share these resources, it's important to, I think, take a look at what the effects are on our system that these agricultural productions are producing. So for example, if we take a look at water use in California, we can see that there's 3 major sectors where water is used, and the first is environmental, which is the greatest use, and that's like our forests and wetlands and estuaries, all the natural uses of water, which fluctuates the greatest, of course. But then there's the agricultural sector, which is the second greatest user of water, and on average it uses 40% of the total water supply in California. And of course, during drought years, that percentage is greater. And so it's no wonder that there's a lot of controversy over the distribution of water supplies in California. But maybe more alarming than the amount of water used in agriculture is the effects of pollution on our freshwater aquifers in the United States. Places like the Central Valley in California has seen nitrate levels increase moderate to high nitrate levels throughout many parts of our drinking water aquifers. And then places like Kansas, they've seen nitrate levels at high concentrations throughout the entire state and extending down into portions of Texas. And this is a study done back in the late 80s, and the distribution of nitrate pollution looks similarly today, and then those concentrations are increasing, and the trends can be shown on the right plot, and this is work done by Scanlon and others where they looked at concentrations measured in nearly 1,500 wells in Texas. And they looked at those concentrations before and after agricultural development in their state. And what they show is that the nitrate concentrations have grown by a factor of 3 in response to agricultural development. So to put that into context in terms of trends, there's another study by Howarth and others, and they looked at total fertilizer use in the United States. And what they've shown is that since 1960 to the year about 2000, the amount of fertilizer use has increased by a factor of 3. And that if you project that forward using business as usual kind of scenarios, they're expecting the amount of fertilizer use to double again. And as you can imagine, the nitrate levels in groundwater are going to increase significantly in response to these increases use of fertilizer. And given that nitrate measurements on wells are, the median values are well over 4 milligrams per liter in many areas, it's not difficult to imagine that the concentrations are going to increase above 10 milligrams per liter, which is the maximum contamination level for nitrate in drinking water, which represents significant health risks, especially for children. But something else that's really interesting about this plot is that they show projections for agricultural changes in what agricultural productions are towards more in line with the Mediterranean diet. And what that means is that we grow more fruits and vegetables and grains and much less meat. And if we follow those kinds of scenarios into the future, we can reduce fertilizer use in half just from changing the food that we produce. So that's another reason to become a vegetarian. Another aspect of pollution related to agriculture, especially in coastal areas, are the effects of saltwater intrusion. And some of the most productive areas in California are the river basins and the coastal areas. And this is an example in Pajaro Valley where they measured groundwater levels throughout their basin over a period from 2011 through 2013. And they've shown through the changes in the colors in red there that the areas within the basin where groundwater levels are well below sea level has spread all the way to the margins of the basin. So most recently, they measured that groundwater levels are about 30 feet below sea level over a large portion of this basin. And so when you take models and you simulate the effect of that saltwater intrusion moving into the basin, they're projecting that the saltwater is going to move well into the basin in the next 2 or 3 years, which is pretty scary, considering that this is a very productive basin and their production is going to decrease significantly if their water degrades that much. So the hope is that we get a really big year and we get enough recharge to fill in all that storage in that aquifer so that the seawater doesn't do that. Another important resource that's used in agriculture is energy. Energy uses about 4% of the total energy use in California, which seems like a modest amount, but when you put that into context, shown on the right, on the graph on the right, with the timing of when energy is used, it corresponds to the peak energy use in other sectors. And what that means is that the power producers have to turn on what are called peaker plants. And the peaker plants tend to be coal power plants, very old and dirty and inexpensive. And so what that means is that reductions in energy use by the agricultural sector, and this is basically pumping groundwater for irrigation, if they can reduce their groundwater pumping, they can have a significant reduction in the amount of carbon in their carbon footprint. So in addition to the benefits of sustaining their aquifer systems, there's another benefit of reducing their carbon footprint. So now I want to just go over a few more slides to talk about how agriculture is susceptible to climate. This is probably an equally difficult problem to deal with as we move forward, and also could create a significant problem. So if we take a look at the historical climate over 2,000 years, and this is a graph showing the climate reconstruction using the Palmer Drought Severity Index. If we look at droughts over the last 2,000 years, we see that there's been these mega droughts that have lasted 100 years or so. And we can imagine if that happened now, there would be a complete collapse of our society. But maybe more realistic are these droughts that happen after these large mega droughts that are, consistently as long as a decade long. So we're only really 4 years into this drought, and we can only imagine if we went another 5 or 6 years, what the effects that would have on the amount of food that we're producing in the western United States. And just this year they reported on the radio, I was listening, and there was a study showing that the amount of lands that are fallow in California are as much as 1/3 of the total agricultural area. Other looming signs of drought in the past, 60-year-old trees at the bottom of Fallen Leaf Lake, relics of a mega drought that happened in the past, as well as stumps growing 30 feet below the natural rim of Lake Tahoe, all indicators that there is a significant probability of having a big drought that could really affect the amount of food that we can produce in our region. So what my point is, what I'm trying to say is that California and the U.S. as a whole are really an agricultural powerhouse. It's very important for producing food and feeding the people of this world. However, the industry is highly susceptible to two really important looming issues. One, of course, is drought, and the other is groundwater pollution. Essentially agriculture is compromising our water resources in the West especially. And, the positive side of this is that I think there's still much we can do in science and policy to try to improve the situation. Because right now it seems that because everything is driven by economics and we're not considering the costs on our resources, we're paying a pretty heavy price. And that's becoming more and more clear during this drought. So here's a plot that I found in a paper by English and others, and I really think that this work demonstrates a huge potential for improving efficiency in irrigation systems. And what he's showing is that, that the maximum yield as a function of the irrigation amounts actually occurs at much less of an application rate than what most farmers are applying. And so what he's using this variable, it's called the relative depth of applied water. And what that means is that you apply enough water to your field so that 90% of your field is not at water deficit. So there's plenty of water for the plant over 90% of the field. And most farmers tend to apply more water than 100% RW. And what this work is showing, and this is based on empirical data measured at various agricultural areas, that in general, the optimum yield occurs more like 60% of the total water application. So what is this saying? This is saying that we need to grow food over larger areas and water less. And there's a significant benefit to that, as I'll show, and that is in terms of groundwater pollution. And so this is actually a win-win situation. We can produce more food for a lot less water, and we can reduce our groundwater pollution significantly. And what this plot is showing is that each of those curves represents decreases in the amount of irrigation. And as you step down along those curves, you see the observed concentration, the mass loading of the aquifer is reduced significantly. And overlying on that are measurements in groundwater. So this is consistent with the empirical evidence. And in addition to that, what it also shows is that as you apply less fertilizer, you're also reducing significantly the amount of pollution to the aquifer. So two big factors, reduce fertilizer and reduce irrigation amounts. And coincidentally, when you irrigate less water on these fields, you need less fertilizer. So basically, the take-home point here is that we need to somehow encourage the agricultural sector to water less. But I think the truth is that, you know, growers are a lot smarter than you would think, and they're already doing this in a lot of ways. And this plot shows, and I know it's hard to read, but the blue curve represents a transition from flood type, or the blue curve is flood type irrigation technologies, and you can see that it's sloping down significantly. And then the green curve, which is replacing those flood type technologies, are dripper based technologies. And so this is improving the efficiencies, but that's different than what I showed earlier. What I showed earlier is just basically deficit irrigation. So if you go to deficit irrigation, which what I was showing in that earlier plot, and you improve your technology, then you get savings from both aspects of the problem. So it's a win-win situation there. And I just circled this. This is from a website, and I just thought this was funny because the title of the website is "Agriculture is using 80% of water use in California. Why aren't farmers being forced to cut back?" And that's interesting because, of course, they are really cutting back because they don't have nearly as much water, and they're not using 80% of the water. But that's the kind of, you know, stuff that's been going out there. So what I'm saying is let's reduce the impacts of resources and reduce susceptibility to climate. And how can we do that? Well, what I'm saying is growers need accurate forecasts of water supply, and they need to know how much energy it's going to be required for their irrigation technologies. And growers need day-to-day information about their irrigation performance and the plant potential uptake. So this is where it gets into the modeling, the hydrologic modeling, and climate modeling. So the first aspect of this problem, growers need accurate forecasts for water supply and energy requirements. So the questions here are, how much surface water and groundwater will be provided? So how much snowpack, how much water is going to be delivered to their farms in the form of stream surface water flows, and then how much supplementary groundwater pumping is going to be required, which then allows them to predict how much energy demand they're going to have. And then the last part is, what will be the plant water demand? What's the climate going to be like? So then they can expect, they are going to know how much water they're going to need to produce the plants. So what we're developing are software tools using integrated models to help provide these types of forecasts. And essentially what we're doing, and you know, this is a very kind of standard approach where you take climate modeling that's used for forecasting, they use for weather forecasting and long-term climate change impacts using global or regional climate models. And then that information is provided to your integrated hydrologic operations model. And the hydrologic model simulates the natural flow and distribution of water in these systems caused by gravity. And then ModSim, which is the operations model, represents the effects of anthropogenic distribution. So reservoir releases and diversions off of the main stem of the river. So those two components together account for the effects of both supply and demand on the water system. And then we have the hydrologic model provides the depths, the groundwater levels, and the amount of surface water delivery. And then the difference between the demand and the surface water delivery is the amount of groundwater pumping that is required. So we can then use that information in our energy cost module to make a prediction of how much energy is going to be required in that forecast. And then that information is very valuable for the power generators because they can plan for those demands. Then that's all wrapped into an updating, because every month that goes by, you can improve the predictability of your model by updating with a model with the latest climate information. So by updating that model, we can increase our fidelity of our projections. So this is just a little more information about the hydrologic model and the coupling to the operations model. This is basically what an operations model does is it takes the water laws, so the priorities and the rules of water delivery, and then the demand side, and it makes the decisions about what gates they're going to open and how water is going to be delivered to all the different farms in the system based on those priorities and demands. And then that information is then fed to the hydrologic model, which then simulates the distribution based on the physical processes, mainly gravity. So what we get is snowpack simulations, predictions about how the snowpack is going to develop through time. And then that is fed to create the flow in the stream systems. And we can predict the flows. And then those flows are then delivered to the agricultural sector so that they can make the planning of what fields to plant and how much water they're going to have to pump. And in these modeling approaches, as long as we have good information about precipitation and temperature data, we can do a good job in simulating the snowpack development and melt. And this plot on the left shows the comparison between the satellite imagery of the snow-covered area versus the model. And as you can see, we can match those processes relatively well, and we can simulate the stream flow relatively well. So what the key information here is what is the demand and how much, what is the climate information. So we want to be, that's why it's important to update the models through time. But the big challenge here, I mean, we have the technology, we have the tools, but the challenge is that there's a lack of transparency in the agricultural sector. So we're always looking for data. We don't have the pumping records, we don't have the stream flow information, we don't know how much water they're applying. And there's a perception in the agricultural sector that we're trying to control them. And I remember when I was working in California, I was at UC Davis, and every day we'd drive out and measure the water levels in these wells in these farmers' lands. And one day, instead of driving the UC Davis truck, I drove the USGS truck. And as soon as I showed up, I got out of the truck, and he said, "Oh, no, no, no. You're not coming onto my property, and you're not measuring my well." And I think that really epitomizes the kind of the situation that we're facing, is that farmers are afraid of what we're going to do if we know how they're using these resources. And somehow we need to change that perception, because it's good for all of us if we have this information. And it's going to help the farmers as well, because if they have good predictions of how to improve their efficiency, then they're going to make more money as well, and they're going to have greater sustainability. Then, of course, this is another aspect of the data limitations that we have, is that we don't know how much groundwater they're using versus surface water. And this is a very big problem, because we can't project how much groundwater availabilities are going to be, and we don't know how the aquifers are recovering during drought periods when we move into a wet period, because we don't know how much they're pumping. And so we really need to implement the technology so that we can provide information about groundwater money. And so, the question is, how can we incentivize the agricultural sector to become more transparent? And the ideas that we have are, maybe if we produce tools that benefit them and save them money, that they will in turn provide the data and information that those tools are providing to them. And the other side is that's been used in various parts of the world are energy tariffs. And energy tariffs, if you look in the literature, basically they haven't worked very well. And especially in California and in Nevada, they haven't worked very well, because we already subsidize energy use in agriculture, and we didn't ask for anything back. We gave them big discounts on energy, but what we should have done is say, look, we'll give you this tariff, this discounted energy use, but please give us the data so that we can use that information ourselves. We needed to make a negotiation, and instead we missed that opportunity. But it doesn't mean we can't do something in the future. And then, of course, outreach is always a big component, and we need to talk to folks more out there and get to a position where we all realize the problem. This is a shout out to Justin's work. Metric and measuring, consumptive use on a near real-time basis is just a huge technological step forward in terms of improving the environmental sector. And, Justin's group they're developing tools that can quickly provide the information about consumptive use. And the reason this is so important is, historically in California, they use crop coefficients, and it gives pretty good estimates about crop consumptive use. But what metric gives you is on-the-ground evidence of how consumptive use is changing in response to farm behavior. So, if we, create new technologies that should improve water efficiencies, we're going to possibly see that with metric. And I think that's why the work that Justin and Charles and his group are doing is so important. And, one of the big questions is, how can we distill that data to make it so that it's useful for farmers? And I just have a mock-up here that, we're kind of still developing on this concept, but essentially this is kind of an idea from, the Prius. If you've ever driven a Prius, it's kind of really fun because you're watching, how good your fuel efficiency is relative to your behavior. So you start, slowing down before the stoplights, you start taking off slower, all these behaviors, and you can see right in front of you how that is affecting your efficiency, your fuel efficiency. And I'm thinking that, maybe we can do something like that in the agriculture sector. Maybe if the farmers can see how their behaviors are translating to efficiencies in water use, maybe there'll be a benefit there. And I really don't know. I'm not a farmer, obviously, but it would be great to kind of try different ways of presenting this information that farmers can use it and maybe help them improve their efficiencies. Then we have these tools. We have flow meters on their wells. We're measuring consumptive use, and we know how much energy they're using. We can then take that at the farm level, and if the farmers are willing, we can then take that information, upload it into our regional scale model, and have a tool for regulators so that they can have a sense of how well the system is doing and how much sustainability they can expect moving forward. So that was kind of an overview of the tools and ideas that we have moving forward. And now I just want to kind of show you some results of some recent work that we're doing with these models, where we're looking at some scenario testing. So, different concepts to try to help improve efficiency and water availability in agriculture. And this is something that we're calling AGMAR, so Agricultural Managed Aquifer Recharge. And the concept here is that, we get these huge winters around here, and then all that water goes to the sinks, the bottom of the basin, and evaporates away. And I know there's benefits to the environment, but in California, all that water just goes to the ocean. So how about, everyone's thinking about, let's capture that water and let's recharge our aquifers. We got a lot of storage underground. We don't have land storage on the ground, but we have a lot of storage on the ground. But the problem becomes, well, how do we recharge aquifers? Land is so valuable in California, we can't afford to cover it in a bunch of ponds. And so the idea here is, well, why don't we use all of this agricultural land to recharge the aquifers? In the wintertime, when these lands are fallow, why don't we irrigate when the ET demand is low and recharge these aquifers? And we already know that this is happening already. There's a lot of recharge contributed by aquifers. So the idea here is, can we realize benefits in terms of water supply by irrigating in the winter? And this is just an example that really illustrates this, boom and bust type of climate that we experience, that we're all very familiar with. Here's the test model that we're using. It's very much like all of the agricultural basins on the Humboldt or the Walker or the Carson River Basin. This is very typical. We're modeling this with that coupled operations hydrologic model, so we're representing the priorities. So each of these different command areas so there's 4 command areas you can see in those different colors. Each of those have a different priority. And in fact, the lowest one on the system has the highest priority. So he gets his water or she gets his water before the other agricultural systems. And so if you look at the darker colors in each of those ag areas, those represent where we're doing winter irrigation. And in order to do these types of simulations, we have to resolve the actual relationships between water supply and evapotranspiration. So we have to break apart the potential component and the reference to the type of crop they're growing, as well as the supply component. So we're breaking those up so that we can realistically represent the relationships between water supply and plant consumption. And then there's the reservoir component. And so what we're doing here is if you see the red lines that stretch up high towards the plot, those represent the natural flows. And then the blue curves represent the capture of those high flows. And so there's 3 of the command areas have water rights to the reservoir. So they call that accounts. They have reservoir accounts. And you can see that command areas 1 and 2 and 3 have those different accounts, the green account and the orange account. And so all of those effects on how much water is delivered to the farms is incorporated into this system, because we really need to be able to incorporate the priorities of the water distribution in order to realistically simulate the benefits of this artificial recharge, because otherwise we won't really know how that water is distributed once we have that beneficial use. So one of the interesting aspects of this problem that we've, along the way, and this is work that I'm doing with Eric Morway, where we tried to couple the model by just, on a time step basis, just run the operations model, take that information, put it in the hydrologic model, and then distribute the water, and then move to the next time step. And what we found is that when we did that, we couldn't conserve water in the modeling system. And that's important because all the previous work on this topic, they have not coupled these models. And so the question is, how have they been realistically conserving mass in their systems? Well, the truth is they haven't. And so what this plot shows is the yellow boxes represent the iterations that are taking during each time step. So the feedback, the nonlinear feedback between the models is, and you can see by the changes in those bars within each of the yellow and white periods, you can see the diversion amounts are changing significantly through those iterations. And so in order to realistically represent the effects of operations in this hydrologic model, those systems have to be fully coupled. So these are the results for each of the different command areas, where we're showing those lines represent the average depth to water within each command area. So, there's a lot of variability in the groundwater levels within those agricultural areas, but if we take the average, the red lines represent the non-winter irrigation, and the blue lines represent the irrigated area. And you can see that there's benefits to some of the command areas, but as we get lower down in the system, the benefits decrease. And this seems somewhat modest, and so what I wanted to do is take a closer look. And if we take a closer look, the average groundwater levels beneath command area 3 are 3 feet greater than they would have been otherwise. So wintertime irrigation during these large precipitation years has given us 3 feet more of groundwater storage spread over that entire command area. So we're talking hundreds of acres, 3 feet deep more of water, which is very significant. It's a lot more water. So I think this is a promising result, and we have a lot more to do, of course, to evaluate different aspects of this problem, such as how to optimize where we're recharging, the timing of recharge. What are the thresholds of winter irrigation versus non-winter irrigation? And what are the third-party impacts? So could doing this kind of winter irrigation actually have a negative impact on stakeholders within the basin? So there's a lot more to do, but I think it's promising. So finally, I just want to make some final statements about what I think that these results suggest. So finally, there's still much to be done, I think, to improve efficiency in agriculture. I really think there's a lot of benefits in using the simulation software to help the agricultural sector. Of course, we need data, so that means we need more transparency by growers. Coupled operations hydrologic models, I think, is a very big step forward in terms of technology for regional scale regulation of these systems. And then finally, just one type of scenario that we looked at, I think this concept of AgMar could have a great potential, especially in California, where they have a lot of fallowed lands where we can increase aquifer recharge. So that's it. Thank you.